Hello students, today I am delivered the lecture about the operation amplifier with feedback topologies. So operation amplifiers are the amplifiers which are generate and perform some mathematical operations like addition, subtraction, multiplication, integration, differentiation, and amplified the output in terms of input voltage, then so it is called the operational amplifier. So we have used the operational amplifier as an active device in terms of open loop configuration or in closed loop configuration. When we use in open loop configuration, then it is used as an active device, so it is produces the high gain in the output. So when we use in open loop configuration without any feedback, then it is used in three ways. First in differential amplifier, second one is inverting amplifier, and third one is in non-inverting amplifier. So we use in first the diagram when I have shown here in way of differential amplifier, means in this way in the non-inverting and inverting terminals we have provide the voltage source Vin1 and Vin2 with series resistance Rin1 and Rin2, and the output which is generated in terms of difference of the input, that is output multiplication of gain into V in minus V into. Suppose V1 and V2 are the two input of the difference voltages, then V1 and V2 are the voltages of input terminals, then output is in terms of difference of it. So output is equal to A into V1 minus V2, or here we will use the supply VCC and minus VE. Second one, when we use in terms of open loop configuration inverting amplifier, so in this case we have without any feedback use the source at non-inverting terminal and other inverting input source at inverting terminal, and the output source other source that is called the non-inverting terminal, which is grounded. So in this case when these voltages are V1 minus V2, and suppose in this case when we provide the input as inverting terminal, so output is generated in terms of minus A into V input voltage. Here minus indicates that the output is phase reversal of the input voltage with respect to 180 degree of the input. Third one, when we use the open loop non-inverting configuration, means we have applied the input at non-inverting terminal, so inverting terminal is grounded. So when we take the output, that is difference of input, when we provide the V1 in terms of Vin and V2 is equal to 0, so that V1 minus V2, that is provide the V0 is equal to A into Vin. Vin is our difference voltage, that is Vn. So means output plus sign indicates that output is same phase with the input voltage. So it is the open loop configuration of the three ways. So when we use the open loop configuration, we have produced the large gain, but we have produced some different limitations, that is the saturated output, susceptible to noise, temperature dependency, and other dependencies like power supply variation, mass production, that are also affected, and less bandwidth. So when we introduce the concept of feedback, means when we use the op-amp, output is not constant in a open loop configuration, because due to the non-linear characteristics it is generally affected by some temperature variations and some other variations by which it is affected. So we will use in feedback concept by which we have used the some fraction of the output and giving in the input in terms of some linear element or directly coupled. So when we use the output giving in the input in two ways, in terms of negative feedback and in positive feedback. So that is the example of negative feedback, where we use the fraction of the output and giving in the input via some feedback network, and op-amp is our active device. So in this case when we use the negative feedback, so it is in opposite phase, so it is regenerative feedback, means it is provide the negative feedback to the input source. And other way, when we use the output in terms of same phase in the input, so it is called the positive feedback. So when we use the positive feedback, our gain increases. When we use the negative feedback, our gain is decreases. So here when we use the negative feedback, our voltage gain is reduced, but we have some different advantages. means self-correcting ability, gain stabilization, increase the bandwidth, decrease in harmonic distortion, noise voltages, non-linearity, reduce the temperature power supply variations, and we use the disadvantages are the voltage gain reduce, and for high order systems it may result in unstable system. So when we use the op-amp as a feedback, then we will use the four type of topologies where op-amp as an active device, and we use the some other feedback network by which we have produced the fraction of the output giving with respect to input source. So there are basically the four topologies, that is the voltage series, voltage shunt, and current series. So here I will first take the voltage series, where that is the example of it, where output is the voltage and giving in the feedback terms with respect to series in the input, that is called the voltage series. That is the current series, means we take the output in terms of current and feedback in series with the input source, that is gain, that is called the current series. Third one is voltage shunt, means we have take the output in terms of voltage and shunt with input, means in parallel with the input, mixing is parallel with the input. So it is called the voltage shunt. And last one is that is called the current shunt, means we have take the output in terms of current and also in with input source in parallel way, means shunt way, that is called the mixing shunt way, that is called the current shunt. So these are the four topologies we have used with the op-amp. So first, when we have take the example of voltage series, that is basically the op-amp in non-inverting configurations with feedback. So here we take the output in terms of voltage and via the feedback element giving in series with the input voltage source, that is the example of non-inverting feedback for voltage series topology. So it is the simplified way where we use the op-amp and provide here the VID is the difference at a non-inverting terminal. So here the feedback circuit, that is our parallel combination of R1 and RF, where V0 is the parallel taken across R1 and RF, and VF is taken only across R1, which is our feedback circuit. So it is also a simplified way. So in this diagram where we use the non-inverting terminal, so here put the source at the non-inverting terminal and inverting terminal is grounded, and we have provide the feedback in terms of voltage output in series with the input source, that is the voltage series example of non-inverting amplifier, operational amplifier with feedback. So here in this case we have take the output means beta factor in terms of Vf upon V0. So it is the Vf upon V0 is equal to R1 upon R1 plus Rf, and the total gain V0 by Vs, that is in terms of exact expression A into R1 plus Rf, R1 plus Rf plus A into R1, where A into R1 is more greater than Rf plus R1, so neglect here. So generally I will take out the result in terms of AF, that is 1 plus Rf by R1 for this voltage series feedback topology of the op-amp with feedback. When we use the op-amp in voltage shunt topology, so in this case we have used the inverting amplifier with feedback. So in this case we have take the output in terms of voltage and shunt with the input mixing. So it is called the voltage shunt topology of the operation amplifier with feedback. It is a simplified way where we provide the input at inverting terminal and non-inverting terminal is grounded, and that is the shunt voltage terms which is provided at the input in shunt way. So it is more simplified way where we use the inverting terminal providing the source Vs here and feedback V0 in terms of shunt way with respect to Is and If, that is the parallel conditions of current. So Ib1 is equal to 0. So it is the inverting amplifier with feedback is the voltage shunt topology. So here the gain, that is exact expression minus A into Rf upon R1 plus Rf plus AR1, where AR1 is more greater than R1 plus Rf, so neglect here. So means A to cancel and minus Rf by R1 is our gain with feedback in approximate expression. So here I will tell that these are the comparison values of voltage gain, that is AF minus RF by RF in non-inverting amplifier, and in non-inverting amplifier that is 1 plus RF by R1. Input resistance, when we use the non-inverting amplifier. So non-inverting amplifier, we will use the voltage series, and in always when use the series technology, in this case input impedance always increases with the D factor, means RF is equal to Ri into D, and D is equal to 1 plus A beta, that is D sensitivity. So RF is equal to Ri 1 plus A beta. And in case of inverting amplifier, that is used in the voltage shunt topology. So in this case, that is basically in series we have increasing the input resistance, but in case of shunt topology we will decreasing the resistance, so it is nearly equal to value of R1. In case of output resistance, when we use the both are the voltage topologies in case of inverting and non-inverting amplifier. So in this case of voltage, we have when we talk about the output resistance, so output resistance always decreases by the factor of D, means R naught divided by D, means R of F is equal to R naught 1 plus A beta in case of inverting, and as well as also in case of non-inverting, that is R naught upon 1 plus A beta. Bandwidth, that is F naught 1 plus A beta by K, where K is equal to RF upon R1 plus RF in inverting amplifier, and in case of non-inverting amplifier, that is F naught 1 plus A beta. And the total offset output offset voltage, that is plus minus V saturation divided by 1 plus A beta in both the cases of inverting and non-inverting amplifier. Thank you.